Hello again. You know, when you study exponential functions, a lot of the things in real life follow this exponential growth or exponential decay. Like we talked about the damn virus. In fact, diseases spread exponentially through the population. You know, populations breed and grow exponentially. Populations of bacteria, populations of people, populations of rabbits are famous for growing and reproducing exponential growth. Radioactive substances decay exponentially. Money, when you put money in a bank and it earns interest, it grows exponentially. And so we do a lot of these word problems with money, with compounding interest. So this is this formula. A equals P, capital P, 1 plus R over N raised to the NT power. So there's the exponent up there. Let's talk about this a second. A is the future amount of money. So this is money deposited in the bank, and A is the future amount of money. P is called the principal, which is the original amount of money. So you start with a certain amount of money here. It's like the y-intercept. And then R is the interest rate. You know, it could be a 6.4% interest rate or a 10% interest rate, or it's an annual interest rate. So then T is the number of years you leave it in the bank. If this is an annual interest rate, a yearly interest rate, then T should be in years. So the time should be in years. But then there's this funny thing, N. N is the number of times the interest is compounded per year. So the bank divvies out that interest to you. It could be once a year, and then N is 1. It could be monthly. If they compound monthly, that's once a month, and then N is a 12. If they do it quarterly, they say sometimes the interest is paid quarterly. That's every quarter of a year. That's every 3 months, but that's 4 times a year. So N is 4. So N is this number. It's the number of times then. So the problem should tell you that. So let's try one. Let's say I have $5,000. I put it in the bank. I have an interest rate of 8.64% interest. That might not have been a good number. Let's say it's compounded quarterly. Let's say it's compounded quarterly. And I leave it in there for 20 years. So the question is, how much money will I have? So let's try it. Let's see. Here we go. It's definitely a calculator problem. I'm going to look for A. That's the future amount of money. The principal is $5,000. I plug in there. Here goes 1 plus the R, the interest rate. Now, when you use this formula, you have to make that percentage a decimal. Do you know how to make a percentage a decimal? You move it over twice. That's 0.0864 divided by N. And what is N? If it's compounded quarterly, we talked about N is the number of times it's compounded per year. You got to read the subtle words. When it's compounded quarterly, N is a 4. So I'm dividing by 4. And then I'm going to raise it to the N times T. That's 4 times 20. I guess that's going to be 80. So I definitely need to pick up my calculator and work on this problem. I would divide this and then add it to 1. I'm going to try that. You can try it with me. Let me try that. 0.0864 divided by 4 is a little 0.3456. That's what I got. No, I screwed that up anyway. Hang on, this might help. 0.0864 divided by 4 is a 0.0216. When you add it to 1, you get a 1.0216. That's my base. I'm going to raise that to the 80th. And then I'm going to multiply by 5,000. The 5,000 is not raised to the 80th. You got to be careful of your exponentiation and your order of operations. So now again, I need to know how to use my calculator. There's different ways to do this. Sometimes you do 0.0216, 1.02 raised to the 80th. Sometimes you have this on your calculator that helps you exponentiate stuff. Or I said you might have an X to the Y button where you type in the base, you hit that button, then you type in the exponent 80, and you hit it equals or enter. So there's a couple different ways you use your calculator to exponentiate. Here I go. I'm going to raise this to the 80th. Wow, 5.52 something, 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 something. When I multiply by 5,000, I'm going to multiply by 5,000, and the answer is, here it is, $27,633.81. This is money in dollars, and we should round to the hundreds place. We should round to the cents. So, cool. That was fun. You should practice that. You know, I'd like to point out something. You know, the interest rate was 8.64%. So that's like a 0.08. Seems like we should be multiplying by 1.08 every year. But remember, we're not doing it every year. We're doing it once every quarter, 4 times a year. So we take that yearly rate and divide by 4. And that gives us, so we're only giving ourselves a quarter, 3 months worth of interest. Oh, and then we're doing it 4 times a year for 20 years. So we're doing it 80 times. I'm just trying to help you make sense out of why this formula makes sense. But anyway, there it is. I do nothing for 20 years. I put that money in the bank and it grows. It earns interest. And the interest it earns gets deposited in there and it earns interest. That's the phrase compounding interest. The interest that it kept earning every 3 months, that little bit of interest it kept earning kept going, added to the principal, and it earned interest, and we have this compounding interest. You know, there's this other phrase. There's another phrase. I'm gonna erase this. I'm gonna erase this. There are some cool problems where we do compounded continuously. I think these are a little later in the chapter, to tell you the truth. I think all the ones in section 5.2 use this formula. But while we're discussing this, compounded continuously. When you compound it continuously, that's like every split second. Hang on. If it's compounded monthly, n is 12. If it's compounded daily, n is 365. If it's compounded every hour, it's whatever, 24 times, it's huge. However many hours are in a year. If it's compounded every minute, that's huge. If it's compounded every second, that's huge. So when it's compounded continuously, it's like every split second, and n goes off to infinity. And when n goes off to infinity, you can prove this with calculus, but you do a new formula. You get this formula, P(e) to the RT. There is no n. N went off to infinity, and the base became e, which is that famous number, 2.7, blah, blah, blah. So let's do this same problem. Let's just say it was compounded continuously. When you see that phrase, again, this might be a little later in the chapter, you use this other formula. And we're going to get more money because we got more interest compounded earlier. But the truth is, it's such a small amount of interest, it won't be that much more. Let's do it. Here we go. We got the $5,000. We got our base E raised to the interest rate times the 20 years. The interest rate was a 0.0864, and that's multiplied by 20. And that's all the exponent on the E. So you got to be careful how you do this. Let me try this here. 0.0864 times the 20. So that's a little 1 point, so I'm getting E to the 1.728. So I find my E button. It's right there. Second ln is the E button to the 1.728. And I get 5.629 something, 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 something. Anyway, that's multiplied by the 5,000 here. So this turned into this, this turned into this. You multiply this times 5,000. I just do it in my calculator. And the answer is $28,146.92. So it is more money. We knew it was going to be more money. Remember, I said it was not that much more. What's that? Yeah, roughly $500 more after 20 years for compounded continuously. But it's kind of an easier formula to use. I mean, it uses this number e, but it's a little easier to use. You don't have to deal with the n. You don't have to deal with dividing by n. So I like that. Let's do one more thing while we're here. I'm going to get rid of all this. Get rid of all this. I should warn you when I'm about to erase, maybe you can hit pause and take some notes or write something down before I erase. Sorry I didn't warn you. Here's what I want to do now. Let's just, part B of that question, let's say we're compounded continuously again. Same problem, same thing, not this anymore. We're compounded continuously. And now part B says, when will I have $1 million? Ha, 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 ha. When will I have $1 million? So now what do you do with that formula? Here, let me write the formula down. The formula was this. Now I'm looking for when is it going to be $1 million. I'm looking for when this is going to be $1 million. What's the original amount? 5,000. E, the interest rate is 0.864. And I'm looking for when, so I'm looking for the time, the number of years it takes. So I've got to solve for t. Okay. Let's see, we got to do a little algebra. Maybe we know how to do this. First step you know how to do. Everybody knows how to divide by 5,000. Divide by 5,000. It's gone. Divide by 5,000. I think I get 200. Yeah, 200 equals e to the 0.0864 t. Now I've got to undo the e. In order to solve for that t, I've got to get rid of the e. I taught you this a minute ago. You need the inverse of an e function. You need the natural log function. So you take the natural log of both sides. Even though I haven't taught you exactly what that is, it undoes the e function. The natural log of the e cancels out the e, and it leaves me with this 0.0864 times t. Now anybody can solve for t. This is the natural log of 200. You would divide by that decimal point, and t is the natural log of 200 divided by 0.0864. Now be careful how you do that. You do your numerator first. You do the natural log of 200, then you divide by that decimal. You pick up a calculator, put on your glasses, pick up a calculator. The natural log of 200 is not that big a number. It's just 5.29 something. When you divide by 0.0864, I'll just write that for you, 5.29 something, 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 divided by 0.0864. That's going to lead me to the answer. I'm going to divide by 0.0864, and the answer is the number of years. Wow, 61.3 years. Man, that's pretty interesting. Remember, at 20 years, I had $28,000. And now, if I just wait 40 more years, I'll have $1 million. It exponentiates, it grows exponentially. In 61 years, that $5,000 grew to $1 million at that interest rate, compounded continuously. By the way, in 61 years, $1 million is not what $1 million is nowadays. Inflation has been eating that $1 million, eaten into that percentage. So I don't know. It's not $1 million in 61 years isn't exactly like $1 million is today. $1 million today isn't exactly like $1 million was 60 years ago. All right. Thanks for working and thinking with me.